Welcome to this explainer. I am so thrilled to take you on a journey today into the hidden mechanics of the digital hardware we use every single day. We interact with computers constantly, right? But very few of us actually get to peek under the hood and see the foundational building blocks that make the whole thing tick.
It's a question that honestly sounds almost like magic. How does a piece of metal and silicon actually think? How do we go from literal rocks and electricity to processing complex thoughts, rendering 3D graphics, or, streaming this very explainer? Well, today we're going to demystify that magic by building a digital computer from the absolute ground up. Okay, let's dive into this. Here's our blueprint for today. We'll start with the math behind computers, move on to our building blocks called logic gates, solve visual puzzles with Carnot maps, look at sequential circuits for adding memory, and finally explore the blank canvas of FPGAs. Let's start at the very beginning with part 1, the math behind computers. Before we even touch a wire or a microchip, we've got to talk about the abstract logic that makes computing possible in the first place. And this all relies entirely on Boolean algebra. Way back in 1854, an English mathematician named George Boole proposed this system of logic based purely on true and false states. Now, for decades, this was basically just a philosophical exercise. But then, in 1938, Claude Shannon, who was a researcher at MIT, had an absolutely massive breakthrough. Fun fact here, his master's thesis making this exact connection has actually been called the most important of the 20th century. Shannon realized that Boole's 19th century philosophy could be perfectly mapped onto electronic relay switching circuits. He saw that true could literally just be a switch turned on, and false could be an off switch. It's so simple, right? But this brilliant connection is the mathematical foundation of all digital logic. Moving on to part 2, our building blocks, also known as logic gates. Now let's turn that abstract math into physical reality. What this brilliantly illustrates are the basic Lego bricks of the digital world, the logic gates. These are tiny electronic circuits that produce a specific output based on a simple Boolean operation of their inputs. Notice how each gate, like the AND, OR, and NOT gates, has its own graphical symbol, an algebraic equation, and a truth table. That truth table is absolutely key here. It tells you exactly what the output will be for every possible combination of ones and zeros entering the gate. For example, an AND gate only outputs a 1 if both input A and input B are 1. Pretty straightforward. But by connecting these tiny physical gates together, we actually start to build complex decision-making machines. Which brings us to part 3, visual puzzles, called Carnot maps. So, as you connect more and more of these gates, the circuits get incredibly complicated. We need a way to build efficiently so we aren't wasting our precious gate Lego bricks. Now, if you have a desired computer function, you could try to design the circuit by wrestling with long, boring algebraic equations. But honestly, that's super tedious and really difficult to optimize. Instead, engineers turn this optimization process into a highly visual game. By plotting the desired outputs on a special grid, they can group adjacent ones together. Doing this lets them easily eliminate redundant variables, which means they can get the exact same computational result using far fewer physical gates. Ultimately, it saves space, time, and of course, money. Now, what's really interesting about this slide is how engineers literally draw loops around adjacent ones on these Carnot maps. You can loop 2, 4, or even 8 adjacent squares. And the rules actually let you wrap around the edges of the map, treating the whole thing almost like a sphere. It's pretty wild. Every time you wrap a loop around these ones, you are instantly canceling out unneeded inputs. It's just this beautifully elegant way to strip away the fluff and design the most streamlined digital circuitry possible. Okay, part 4, adding memory through sequential circuits. Up until now, our circuits just react to whatever is currently plugged into them. But to make a true computer, we need a massive power-up, and that is the ability to remember. To understand memory, we really have to distinguish between 2 types of circuits. What we've discussed so far are called combinational circuits. Their output depends purely on the inputs present at that exact moment. Change the input, the output changes instantly. But a sequential circuit? That's an entirely different beast. Its output depends on both the present inputs and its past history. This concept of sequential logic is exactly why your smartphone can remember a saved password, or keep a video paused, or store a document. It gives the circuit state over time. The foundational element of all this memory is something called a flip-flop. Take a look at the truth tables and graphical symbols for the SR, JK, and D flip-flops here. The really crucial one I want to point out is the D flip-flop right at the bottom. It's often called the data or delay flip-flop. What it does is capture the value of its input at a precise moment, dictated by a system clock, and then it just holds on to it. It essentially delays that 1 or 0 for a single clock pulse, which effectively stores 1 bit of data. And by stringing a bunch of these D flip-flops together side by side, we create the very memory registers that are sitting inside the CPU of your computer today.
Let's move to part 5 and see how this builds into the blank canvas, FPGAs.
Historically, early integrated circuits were pretty limited, right? Often having only 1 to 10 gates per chip. Naturally, as tech advanced, we wanted to pack more and more gates onto a single chip to increase computation speed and drive down production costs. But there is a huge catch here. Designing the custom physical layouts and actually hardwiring all these interconnections for every specific new computer function is incredibly expensive and time-consuming. You really don't want to manufacture a completely new physical chip every single time you update a software design or change a protocol. It just doesn't make sense. So the tech industry desperately needed a solution, a general-purpose programmable logic device that could be adapted on the fly.
And that's where the Field Programmable Gate Array, or FPGA, enters the picture. This is, for sure, the ultimate digital sandbox. Instead of hardwiring the gates for one specific purpose at the factory, an FPGA gives you this massive grid of uncommitted logic blocks, surrounded by input-output blocks with a complex web of programmable interconnects between all of them. So by simply downloading a configuration file, an engineer can instruct these logic blocks and interconnects to basically wire themselves up virtually. Seriously, an FPGA can act like a network router 1 minute and then be reprogrammed to act as an artificial intelligence processor the very next. It is entirely adaptable, perfectly bridging the gap between hardware speed and software flexibility.
Which brings us to a pretty mind-bending conclusion. Think about it. We started with the simple true and false math of George Boole. We built basic physical gates, learned to optimize them visually, gave them the gift of memory, and finally arrayed them into these massive programmable canvases. If these simple little gates can remember data and be programmed at will, what happens when you combine billions of them? Well, you get the modern digital world. You get the internet, cutting-edge medicine, global communications, and literally the very device you're using to watch this explainer right now. It is all just ones and zeros, perfectly orchestrated. Thanks so much for exploring the magic of digital logic with me today, and keep learning.